Hello once again. It's Mr. V. Hill here to talk to you today about linear programming. And we're just going to jump right into an example of how we use this nifty little technique. And the example is going to be, well, this problem right here that you see that you all should be very familiar with from the last grading cycle. It was the problem-solving journal problem. And of course, it's all about Mr. Word running his sweatshop. The big idea here is that the problem itself creates a system of inequalities, which we looked at last time, or a little while ago. Specifically, we look down here. We had a parent donated enough materials for a total of 50 garlands. Right? So we need to write a system of inequalities here. The two types of garlands are ones made with small cranes and the ones made with large cranes. So that's what we should probably define as variables. So let's let x equal the number of small crane garlands and we'll let y represent the number of large crane garlands. So if we're going to make a total of 50 garlands, well, they can only be either small crane garlands or large crane garlands. So this leads us to the inequality of x plus y has to be less than or equal to 50. We can make less than 50. I mean, we're probably going to make the total of 50 to maximize profit, just thinking about how this is going to work. But this is reasonable. X plus y is going to be less than or equal to 50. The other inequality going on here is coming from this statement, that it takes one student on average 3 hours to make a garland out of small cranes and 2 hours to make a garland out of large cranes. So this comes back to that whole rate times time equals distance kind of formula thing. It takes 3 hours per crane. If we multiply that by the number, or 3 hours per garland, multiply that by the number of garlands, you're going to get the total amount of time that it takes. And of course, we have 12 students contributing 10 hours of labor each. So that gives us the inequality of 3 times x plus 2 hours per large crane garland times the number of large crane garlands. That's going to be less than or equal to 120 hours. Now, actually, there's a couple of hidden inequalities in here as well on top of these two. Of course, we can't make a negative number of garlands. So we do know that x has to be bigger than or equal to 0, and also y has to be bigger than or equal to 0. So this is the system of inequalities that arises out of this problem. The other thing that we do need to pay attention to is what we're trying to maximize. We're trying to maximize profit. Okay. Now the profit is going to come from selling all of these garlands, and we're going to assume they're going to sell all of them. So the profit is going to come from, well, make $12 off of each small crane garland and $10 off of each large crane garland. So our profit function, P, is going to be equal to $12 per small crane garland times the number of small crane garlands that we sell plus $10 per large crane garland times the total number of large crane garlands that we sell. So here's our profit function. That's what we're trying to maximize given these constraints. And that's what we call the system of inequalities, the constraints on the problem. So for right now, what we're going to do is forget about the profit function. So this is a function of two variables, but the variables, what the x and y can be, come from up here. So the first thing we need to do is actually solve this system of inequalities, which means, of course, that we have to make a graph. So let me put away the problem for a moment. This system of inequalities has two variables, so that means that we are in the two-dimensional coordinate plane. And so what we want to do is, to get the solution to the system, we just graph all of these inequalities and see where they intersect. So of course, these ones are both in standard form, so it's going to be pretty easy to just look for the intercepts. Here, the x-intercept for this top inequality happens when the y is 0. Cover that up, and we see that x is going to have to be equal to 50. So the boundary line is going to have an x-intercept of 50. And of course, if we look at it, the y-intercept, that happens when x is 0. See then y is equal to 50. And we have less than or equal to, so we want to include the boundary. So we use a solid line for that. And this doesn't have to be a great graph here. It's just kind of giving us an idea of what x and y can be. And then we decide whether we want to shade above or below that line. And well, since it's in standard form, it's easy to just plug in a test point like the origin with coordinates 0, 0. So 0 plus 0, that is most definitely less than or equal to 50. So we want to shade the side of the line that includes the origin. All right. Next one that we want to graph is going to be this 3x plus 2y is less than or equal to 120. Again, we're just going to find the intercepts. So when the y is 0, that gives us the x-intercept. 3 times x equals 120, so of course x has to be 40. Right here. And the y-intercept is going to happen when the x is 0. So when 2y equals 120, y has to be 60. So that's going to be up here. And so we just put dots here at those two intercepts, and we decide whether we want to shade it, or excuse me, first we could connect the dots. And we want to include the boundary line because it's less than or equal to. And now we test a point like the origin. 3 times 0 is 0, plus 2 times 0 is 0. Yep, 0 is most definitely less than or equal to 120. So again, we want to shade to the side of the boundary line with the origin. Now, we do have these two additional constraints that just say that both x and y have to be positive, which of course means that we're in this first quadrant. So really, what we're looking at is the intersection point of those two boundary lines. What we end up with, and there's a little angle there, it's a little tough to see, but it's definitely there. What we're really looking at is this quadrilateral right in here. So all the points on these boundary lines and inside the quadrilateral, those are the points that satisfy all 4 of these inequalities. And so this, in linear programming is what we call the feasible region. Oh my goodness, did I spell that right? I don't know whether that's an I or an A. I'll have to look that up, or you can. Maybe that'll be a question on the quiz. So that right there, this quadrilateral is the feasible region. Meaning those are the only points that it really makes sense to even try to maximize our profit function at. Because down here, or at least out this way, either the x is negative or the y is negative. That doesn't make any sense. And up out here, we're going to be making far more than 50 garlands. So it doesn't make sense out here, or it won't satisfy the second inequality as well. So we only are looking at these points right here. So really, we could just test out a whole bunch of points in here and see what's happening. But the whole point of linear programming is that since this is a linear function, the maximum of it, or the minimum of it, can only happen at one of these vertices of this quadrilateral, or whatever polygon shows up as a product of the constraints. Right. So what we really need to do, well, nice here that these four vertices, we already know what they are. Here we've got 40, 0. Here we've got 0, 50. Here's the origin, 0, 0. The only point that we don't know the coordinates of is that little vertex right there. So the way we need to get that, well, that's the intersection point of our two boundary lines. So we just need to solve the system of equations for the boundary lines, where we have x plus y equals 50, and 3x plus 2y is equal to 120. Here they're both in standard form, so easiest thing to do is just use the elimination method. If we multiply this top equation by 2, or excuse me, negative 2 on both sides, it'll be nicely set up for elimination now. So now we'll have negative 2x plus negative 2y is equal to negative 100. And we still have 3x plus 2y is equal to 120. And now when we add the two equations together, really combining the like terms here, the y's are going to cancel out. So negative 2x plus 3x gives us x. Negative 100 plus 120 gives us 20. That's the x-coordinate of this point. So the y-coordinate we get just by plugging back into the original equation. Well, of course, if x plus y equals 50 and x equals 20, then we know that y has to be 30. So now, in order to maximize our profit function, we just check and see what the profit is going to be at each of these four vertices. So at the origin, profit is going to equal 12 times the x-coordinate of 0 plus 10 times the y-coordinate of 0. 0 plus 0 is, of course, just 0. Meaning if we don't sell any cranes at all, we make 0 money. Makes sense, right? Let's check out at this point down here, the 40, 0. Here, the profit is going to be, let's see here, profit function is 12 times the x, which is 40, plus 10 times the y, which is 0, which is, of course, 12 times 40, which is just 480. So here, at this point, we're going to make $480. Let's check this y-intercept point up here. At 0.50, the profit is going to be 12 times 0 plus 10 times 50, or, well, that's 0, 10 times 50 is 500. So if we make all large cranes, we make $500. If we make all small cranes, we make $480. So let's check this point here where we have a mixture, 20 and 30. Here our profit is going to be $12 per small crane garland times the 20 small crane garlands plus $10 per large crane garland times the 30 large crane garlands, which is, let's see here, 12 times 20 is 240 plus 10 times 30 is 300. That'd be $540. So of these 4 points, here's where we get the most profit, $540, if we make 20 small crane garlands and 30 large crane garlands. That's basically linear programming in a nutshell. And a lot of you got this point right on the problem-solving journal, but you have to explain why that has to be the maximum. That's kind of the big deal here. But it has to do with the fact that this is a linear function. Now, I'm not going to try to explain it via video here because now what we have to get into is some three-dimensional imagery, and it's kind of difficult to do in a two-dimensional representation over a video. So in class, we'll talk about that some more, and I'll try to bring some new stuff or explain this with a whole lot of hand waving. Anyways, that is it for linear programming. See y'all in class tomorrow.